Okay, we are off to chapter 8 here. So in this chapter, we're going to talk about some important calculations, and we'll also talk about how to calculate empirical formulas and molecular formulas. So let's get started here. So the first thing we're going to really talk about is the atomic mass, and the atomic mass is one of the fundamental properties of an atom. It's obviously based on how many protons, electrons, and neutrons it has. The atomic mass can be found on the periodic table. It is actually, again, that number that we see on the bottom there is the atomic mass for everything. But when we talk about the atomic mass of sort of atoms, they are very, very small sort of entities. And you can't just kind of pick one up and put it on a scale to weigh them. So in this situation, what they typically will do is pick something that is sort of used as a standard and a standard to compare basically the mass of everybody else to. And for atomic mass, they actually picks the carbon 12 isotope as the standard. And the carbon 12 isotope has 6 protons and 6 neutrons, and it has a mass of exactly 12 AMU. And AMU is a unit of mass, which is an atomic mass unit. And the atomic mass unit is sort of a unit, honestly, that we don't use a lot in calculations and sort of everyday sort of chemistry sort of calculations. But it is really sort of the number that you see on the periodic table. So technically speaking, when you look at that number on the bottom, one sort of unit that is used is this would be 1.008 AMU per atom. And that is one sort of unit of atomic mass. As we'll talk about later on in this chapter, we use a more usable unit, usually when we take that number off the periodic table, which is in grams, since we weigh things out in grams and we get masses in grams. And we'll talk about grams per mole, which is the molar mass, which is a more sort of convenient unit of mass measurement that we use. 1 AMU is exactly equal to 1/12 of the carbon 12 isotope. So basically, what they did was some experiments, and they found, for example, that hydrogen is only about 8.4% as big or as massive as the carbon 12 isotope. So basically, they did sort of a little calculation. This is basically 8.4% converted into a decimal. Divide by 100 or move the decimal place 2 places to the left. And they times it by the atomic mass of our carbon 12 isotope, and we get something like 1.008. So as I mentioned before, you can find all those numbers up on the periodic table. Typically speaking, 4 significant figures is typically what we take off of it. And for any of these, you can use it as this sort of conversion factor, 16 AMU per atom. Once again, we don't often use it very much in those units, but it is sort of a unit that you can use off of the periodic table. Now, when we look at carbon, though, for example, on the periodic table, when we look at carbon, it doesn't actually say 12, but it does say 12.01. And you may be thinking, well, if they use the carbon 12 as the standard and it has a mass of 12 AMU, how come it doesn't say 12 there underneath carbon? And the reason for that is what we actually do see on the periodic table is the average atomic masses, and they're the average atomic masses of all the naturally occurring isotopes for that particular element. So remember that isotopes are the same element, but they have different masses because they have different numbers of neutrons. So all the naturally occurring isotopes for a particular element is used to come up with the atomic mass that we see on the periodic table, although most people don't sort of call it an average atomic mass. It is an average of those naturally occurring isotopes. To actually calculate that, so if you wanted to calculate the atomic mass of an atom in AMU, you would take the percent abundance or relative abundance and times it by, for the first isotope, and times it by the atomic mass of the first isotope. Then what you do is actually add it to the percent abundance of the second isotope times it by the atomic mass of the second isotope. And you continue that pattern depending on how many isotopes you have. You're actually adding here, and for some reason people always want to like multiply when they do this calculation, but you are adding in between those things. The percent abundance or the percent relative abundance is the percentage at which that isotope occurs sort of naturally. So if you have 100% of all the isotopes possible, that would be the different percentages that you would get. They should add up to about 100%. So, for example, if an element consists of 3 naturally occurring isotopes, when you add up the relative percent abundances of those 3 isotopes, they should add up to about 100%, obviously, in terms of percentage. So, for example, if we look at carbon in general, the 2 naturally occurring isotopes for carbon is the carbon 12 isotope, which has a mass of 12, like we were talking about. And that occurs about 99% of the time. And there's also the carbon 13 isotope, which occurs just over 1% of the time. And that has a mass of about 13 AMUs. So if we do this sort of calculation we just talked about, we would take the percentage of our first isotope and essentially convert it into a decimal. And we would times it by the atomic mass of our first isotope, which is 12 for our carbon 12. We would add it, and again, if you don't want to move the decimal, you can divide the percentages by 100 here, and it'll move the decimal place for you, basically. Times it by 13.00335 AMU. And if we do all that together, that is where we get that 1201 number that we see underneath carbon on the periodic table. Questions on that calculation there? Again, as I mentioned before, when you do add up the sort of percent abundances or relative abundances of each of these isotopes, should be somewhere near 100%. If you add them up and it does not equal about 100%, it may not be perfect 100%, but it should be pretty darn close, just a little over 100, just a little under 100. But if you add it up and you're only at like 70%, you're obviously missing 30% for another isotope maybe, or a couple other isotopes. So you could subtract from 100, for example, if you had some other information to figure out the percentage that's missing. Now, it's important to remember that although we kind of consider the atomic mass of carbon to be 12.01, if you could actually pick up all the carbon atoms themselves and weigh them, you would never find one that's exactly 12.01. You would either, for example, in this example here, find one that is the mass of carbon 12, which is 12, or you'd find one that is the mass of carbon 13, which is 13 and some change. So even though that is sort of the mass of carbon, you would never really find one there because, again, it's just an average value of our naturally occurring isotopes. So why don't you try one here? Bromine 79 is 50.70%, has a mass of 79.92, and bromine 81 is 49.32, has a mass of 80.92. What is the atomic? Okay, so in this case, we got a couple of isotopes of bromine. Bromine 79 occurs about 50.70% of the time, and 79.92 AMU is its atomic mass. We have bromine 81. Remember, when we see this dash in the numbers, the mass number we're looking at, which is protons and neutrons, occurs about 49.32% of the time and has a mass there of 80.92 AMU. Again, just a quick look at our percentages, and it's about 100%, a little bit over in this case, but that's okay. Again, we're not obviously missing anything here. So we can calculate the atomic mass based on these 2 isotopes here. And we will end up with, again, on the percentages, you can just move the decimal, which would give you 0.507, times it by 7992 AMU. Again, if you don't want to kind of move the decimal, you could also, as I mentioned before, just divide that percentage by 100 and it'll move it for you, times 80, whoops, decimal in the wrong spot, 80.92 AMU. And if we do that in this particular case here, So 0.4932 times 8092. Gonna get us a atomic mass here based on these guys of 80.43 AMU. In that case, question on that calculation there. All right, let's try maybe another one here. An isotope that is 70.5% abundant with an atomic mass of 117.80, while the other isotope has an abundance of 29.5% and an atomic mass of 120.85. What is the atomic mass in AMU? Again, we got a couple of isotopes. We got some percentages for each of them. Just a quick look at it again. It is about 100%. So we're not missing anything. So we can calculate our atomic mass again here by taking our first isotope and again convert it into a decimal, my percentage. Move that decimal 2 places to the left. Again, times it by the atomic mass of my first isotope. Again, going to add it here for my second isotope, 0.295 times the atomic mass of my second one, 120.85. And we're going to get here about 118.7 AMU in this particular case. Yeah. Maybe that's 10 on the periodic table there. It looks like maybe it's like 10. Any questions on that calculation there? So again, obviously in these couple examples, we had just two isotopes, but if you had three, you do the same thing with just three. Also, you could, if you knew the atomic mass from the periodic table, maybe figured out the percentage of one isotope or the atomic mass of one single isotope as well. Any questions on that there? Okay. All right, so the relationship between atomic mass unit and grams is this. 1 AMU is equal to 1.66 times 10 to the minus 24 grams. As I said before, we will kind of move away from atomic mass units to a more useful unit of grams rather than AMU. We can, though, again, like I said, kind of pull it off the periodic table there and use it as a conversion factor. So once again, if you went to carbon, that is what you would see. Again, in terms of a useful conversion factor, 12.01 AMU over atoms. Or again, you can flip it, atoms on top and 12.01 AMU on the bottom. So if we wanted to know the mass in AMU of 431 atoms of carbon, again, we would use that from the periodic table as a conversion factor. The atoms would cancel, and that would leave us with our AMU in this case. Again, multiplying the top, dividing the bottom there. Same thing here with aluminum. If we take a peek at aluminum there on the periodic table, again, we will see 2698, which does give us two sort of AMU conversion factors, 2698 AMU over an atom. Or an atom is, again, 2698 AMU. Once again, here, if we want to know the mass in AMU of 75 atoms of aluminum, again, using this as a conversion factor from the periodic table, setting up a dimensional analysis. Again, opposites going to cancel. That's going to cancel out our atoms, going to leave us with AMU when it's all said and done. And again, in this case, gets something like 2024. All right, so that is AMU, and like I said, although probably outside of this chapter, you probably won't see AMU all that much. We do use a more usable unit from the periodic table, which is the molar mass that we'll talk about. And we also sometimes will use Avogadro's number as a conversion factor. So, excuse me, let's talk about the first one, which is actually the mole. And in life, we have a lot of sort of words that represent a certain amount of something. So, for example, when you say you have a dozen of something, people know that you mean you got 12. If you say you have a pair of something, people know that means you got two of something. Got a gross of pencils, that's 144. In chemistry, we have a word that basically represents a certain amount of something, and that is the mole. And the mole is abbreviated MOL. And very often confused by people is when they see MOL, they think molecules. And it is not, it is the abbreviation for mole. They had to get rid of something, so they got rid of the E. I would say pretty much in chemistry, if they want something to do with molecules, they will actually spell out the word molecules. So there is no confusion between MOL. So definitely if you see MOL, it is moles and not molecules that is referring to. And a mole something does represent a certain amount in terms of a number, and that is what's known as Avogadro's number, and it contains as many elementary entities as atoms, molecules, or other particles as there is in exactly 12 grams of the carbon-12 isotope. And that number is what is known as Avogadro's number, and Avogadro's number is 6.022 times 10 to the 23. And basically, Avogadro's number is used as a conversion factor to go between certain units. And we could say basically that 1 mole of anything is equal to 6.022 times 10 to the 23. Now, when we talk about the units associated with Avogadro's number, they do change. So they could be particles, they could be atoms, they could be molecules. They could be pizzas, right? They could be shoes, whatever it may be. Although you might get the occasional pizza question, I would imagine that in most cases, these are really the two sort of most common units that are used with Avogadro's number, which are atoms and molecules. And we use it differently depending on what we're using it with. So for example, if we just had like sodium by itself, we would use the units as atoms there. If we had something like water, which is a molecule, we would use the units of molecules. So atoms and molecules are typically used. And really, Avogadro's number is the conversion factor to go between moles and atoms, are molecules, and backwards. So Avogadro's number is that conversion. It is really just a conversion factor. So you could say 1 mole on top, 6.022 times 10 to the 23 atoms on the bottom. And you could flip it around and go 6.022 times 10 to the 23 atoms on top and 1 mole on the bottom. 1 mole of hydrogen would contain 6.022 times 10 to the 23 atoms of hydrogen. 1 mole of sodium would contain 6.022 times 10 to the 23 atoms of sodium. If you had 1 mole of water, like I mentioned a second ago, that would contain 6.022 times 10 to the 23 molecules of water. If you had 1 mole of methane, it would contain 6.022 times 10 to the 23 molecules of methane. So you can use Avogadro's number really with anybody from the periodic table, and that would most likely be atoms would be the units you would use. You could also, again, use Avogadro's number from obviously anything that is a molecule or a compound. I would say that sometimes people use Avogadro's number wrong or when they don't need to use it because they remember this number and they think like maybe I should use it in every calculation. So you definitely don't want to use Avogadro's number in every calculation. You want to use Avogadro's number only if you are given a number in like particles, atoms, molecules, or you're asked to solve for something in atoms, molecules, or something like that. If none of that's mentioned, you really should leave Avogadro's number on the sidelines there, and you should not use it. So those are the keywords you want to kind of look for when you're trying to determine, should I kind of use Avogadro's number in this calculation? Any questions on that there? Now, as I mentioned before, Avogadro's number does represent basically that number, and that represents a mole of anything. And again, just like we talked about a dozen of something, you have 12. When we say we have mole something, we have Avogadro's numbers worth. Now, probably the most common conversion factor that we will use is molar mass. Probably way more than you'll use Avogadro's numbers in future sort of chapters. But molar mass has two units, and it is grams per mole. And where we get the molar mass from is the exact same place we get the atomic mass from. So that number on the bottom, although it is the atomic mass like we just talked about, it is also the molar mass of a compound. And the nice thing about molar mass and atomic mass in AMU per atom and grams per mole is it's the same number. So it actually converts back to the same number if you have it in AMU per atom or you have it in grams per mole. So that makes it really convenient. So for example, here, if we pull this off the periodic table, this would be 1.008 grams per mole would be the molar mass of hydrogen. And really, you could think of it as a conversion factor. You could, if you're doing a dimensional analysis type of problem, flip it around, put the moles on top and the grams on the bottom. Once again, though, if you were asked what is the molar mass of hydrogen, the answer would be 1.008 grams per mole is the answer that you would give. Typically speaking, much like atomic mass, we go 4 significant figures off the periodic table. So depending on what periodic table you're looking at, it may have a lot more numbers. Usually don't have less than that. But if they have a lot of numbers, usually about 4 significant figures, it's a general rule that we use when we take the numbers off the periodic table. And also when we calculate molar mass, 4 significant figures is typically what we usually calculate molar mass to. So kind of 4 sig figs is sort of where we go with this. Now, when you do calculate the molar mass, the number always stays with the grams part, and it's always per 1 mole. So the number always sticks with the grams, and it's always per 1 mole when you calculate the molar mass of something. We can also use molar mass for things that are molecules or compounds. And for example, if we have something like water, if we wanted the molar mass of water, all we simply do is just add up all the parts. So we would go to the periodic table, find hydrogen. We would go to the periodic table, find oxygen. And here we would just add up the parts. So there are 2 hydrogens at 1.008 grams per mole. There is 1 oxygen at 16 grams per mole. So that's my oxygen. That's basically my hydrogens. And if I add that together, it gives me a molar mass for water of 18.02 grams per mole, which is our molar mass of water. Once again, we can use this really as a conversion factor. We can flip it around and do, again, a mole of water up on top, 18.02 grams on the bottom. We want to use it in dimensional analysis sort of conversion. So as I mentioned before, numerically equal to each other, basically AMU per atom and grams per mole are numerically basically equal to each other. And that means we can really pull it off the table. We use more mass more than we use AMU per atom because, frankly, as you know, when you're in the laboratory or whatever it may be, we weigh things in grams, right? So that's just a more useful sort of unit than AMU along the way here. Now, what is the deal with molar mass? Molar mass is clearly your conversion between grams and moles back to grams. So that is the molar mass from the periodic table that allows you to do that. It is also probably the first step in a lot of calculations that you do. And because in a lot of calculations, you oftentimes need to take grams and convert them into moles. Any questions on that there? Now, how does this all sort of tie together? This ties together, for example, is if you have 1 mole of hydrogen, that would contain 6.022 times 10 to the 23 atoms of hydrogen, which would represent 1.008 grams. Same thing if you had 1 mole of water, that would represent 6.022 times 10 to the 23 molecules of water, and that would represent 18.02 grams. So moles is actually sort of the unit that ties together this separation. If you have grams and you have atoms or molecules, it is moles sort of in the middle that ties them both together. Again, if you're going from moles to atoms or atoms back to moles, that's going to be Avogadro's number that you need to use. If you have grams and you want moles, or moles and you want grams, that is the molar mass, again, from the periodic table that you would use to do that. And again, if you have grams and you want moles, you would divide by the molar mass. That way grams will cancel, give you moles. If you have moles and you want grams, you would multiply by the molar mass, doing a little dimensional analysis, and that will give you grams. Same idea over here. If you have moles and you want atoms, you're going to multiply by Avogadro's number. That way the moles cancel, gives you atoms. And if you have atoms or molecules and you want moles, you're going to divide by Avogadro's number. And again, the atoms would cancel and give you moles. So that is how they're all related together. Remember, though, that for Avogadro's number, you don't need to use it unless there's something mentioned about atoms or molecules in the problem. Otherwise, I would say probably 98% of the time, maybe even more than that, this is most likely the conversion factor you're going to use most of the time is the molar mass. Any questions on that there? Now that I wrote all over this here. It's not too important, actually. So the relationship between AMU and grams, like I mentioned before, basically, if you do the conversion, which you don't have to do, basically it makes the AMU and grams basically the same number that you see on the periodic table. Now, Avogadro's number, again, allows us to do those conversions. And again, we can take the mass of atoms and moles of atoms, the number of atoms to our mass of each atom. We could actually calculate the mass of a single atom by using Avogadro's number. All right, so why don't we try one here? Why don't you try this one? How many moles of helium are there in 5.46 moles, grams of helium? For 5.46 grams of helium. There's the molar mass of helium there from the period. Okay, let's take a look. So in this case, we want how many moles of helium are there in 5.46 grams of helium? In this case, it is no mention of atoms or molecules, so I don't need Avogadro's number. So this is really just a conversion of going from grams to moles, and that is the molar mass from the periodic table that allows us to do that. So again, I don't want to use Avogadro's number here because I don't need it. I just need to go to the periodic table, and that really gives us our molar mass of helium, which is 4.003 grams per mole. Again, we could use that as a conversion factor and take a dimensional analysis approach to this calculation. And if we do that, we got 5.46 grams of helium. Again, opposites cancel, which means I actually need to use it in the flip version here. And that's going to give me a mole of helium up on top and 4.003 grams on the bottom. Again, we're doing dimensional analysis, so I'm multiplying the top and dividing the bottom. And that's going to get me there. 5.46 divided by 4.003. Give me a 1.36 moles of helium in this case. Yeah. Any questions on that there? Now, I do want to talk about a little something about here molar mass. It's also kind of an important thing, and it's something that people kind of screw up as well. And that is, for example, if you had something from an equation that's balanced, and let's just say we had, I don't know, we had 2 C2H4 or something like that. And we wanted the molar mass here of this thing. When we would go calculate the molar mass, and whenever you calculate the molar mass, it is always based on the actual formula itself. So it has nothing to do if you have an equation and the coefficient that's in front of it has nothing to do with the molar mass. So if I were to calculate the molar mass of this thing, this would be 2 times 12.01 grams per mole for my carbon from the periodic table. I would then add it to 4 times 1.008 grams per mole for my hydrogens. And that is the proper way to get our molar mass here. Again, sometimes people incorporate a coefficient if they have an equation and there's this thing's in the equation, that would get us something like 2805 grams per mole. This has nothing to do with the molar mass, and that's why the units of the molar mass are grams per 1 mole. 1 mole basically means just one formula by itself is basically what you're calculating there. So that's, again, a very common sort of error. We actually will use this coefficient in a later chapter when we talk about stoichiometry, but when you're doing molar mass, it's always just based on just the formula by itself and just add up the parts. Any questions on that there? All right, let's try another one. What is the mass in grams of one gold atom? Get your gold's molar mass there of 197. Okay, so let's take a look at this. Again, the keywords we're going to want to look at is we definitely want grams, right? We're actually starting with atoms, and that's the keyword there. That means somewhere along the way I'm going to need to use Avogadro's number. And remember that sort of between atoms and grams, what ties those units together are moles. And we would use, in this case, Avogadro's number to get us the moles. And then to kind of go the rest of the way there, we're going to need the molar mass to kind of get us to the rest of the way. So remember that 1 mole of anything, including gold, would equal 6.022 times 10 to the 23 atoms. And again, here we're going to use atoms because we're just talking about an element by itself. That's really going to be sort of used as our conversion factor. So we'll start with our 1 gold atom. Again, doing dimensional analysis here. Basically, gold atoms are up on top. So I would need to put atoms in the opposite location for them to cancel. That gives me atoms and 1 mole of gold. Again, multiplying the top, dividing the bottom, the atoms are going to cancel. If I stop my calculation right at this point, I am in units of moles of gold, which is close to where I want. I got halfway there. Now I need to go the rest of the way, so I will need, again, the molar mass of gold, which can be found from the periodic table. And that tells me there's not 1 point something, 197.0 grams per mole. Remember, again, we're going to just use the molar mass really as a conversion factor. So setting up here, we're still in dimensional analysis. I'm not going to get an answer at this point. You could if you wanted to. I would not round too much, but you could get an answer. We have moles on top, so I do know moles need to go on the bottom here, and grams need to go up on top so that they cancel. Again, still multiplying and dividing, and that's going to get rid of the moles, going to leave me grams, which is what I'm looking for. So essentially, we're going to multiply the top, which is not much there except for 197. We're going to divide it by the bottom, and we definitely want to make sure we're using our exponent button here with Avogadro's number. And we will take 3.271 times 10 to the minus 22 grams of gold would be the mass of one single gold atom, which is a super small number. It's like 21 places to the left, and add some zeros there. In terms of significant figures, one gold atom would be sort of considered an exact number, like something you would count. So you really could go with as many significant figures as you want. So I went with 4 based on the molar mass in this particular case. Yeah. You need to show minimum to get credit the calculation like this. Yeah, that part of it. Yeah. You don't have to, if you're asking, do you have to do all this? You don't. But if it helps, you do it. But for credit, you do need to kind of show that bottom part of the calculation there, yeah, with the setup. Other questions? All right, we will lay that up